Welcome back to Hands-on FPGA Design, from theory to implementation. I'm Albert. Today, we're diving into Lab 2. Following up on our previous lab, where we learned how to control LEDs using Vivado, we're going to take it a step further today. We'll explore how to instantiate Vivado's internal IPs to optimize our hardware designs. As this is our second session, our main focus today will be mastering the utilization of hardware blocks and understanding sequential logic design. Here is the outline for today's session. Before we begin, please ensure that you are fully prepared. For detailed content, please refer to the pre-lab course. There are two core objectives for this lab. First, you'll learn how to instantiate Vivado's internal IPs, and second, you'll practice integrating sequential logic into our custom-designed circuits. The final demonstration will look like this. The LEDs will perform binary counting, where you can flip the slide switches to adjust the counting speed, and press the push button to reset the counter. By doing so, we will successfully implement a fully functional binary counter. This is our experimental circuit architecture. We start with a reference clock input, which goes into a PLL or phase-locked loop to generate two different output frequencies, clock 1 and clock 2. Then, depending on the status of the slide switch, a multiplexer decides which clock domain will drive the LED counter. Think of this setup like a gearbox, allowing us to shift gears freely between the fast and slow clock rates. Finally, the LED counter logic processes the active clock and outputs the binary result directly to the onboard LEDs. Let's take a look at the experimental flowchart. In principle, the overall structure is quite similar to Lab 1, but we've added a step to instantiate the IP core, which is the main focus of today's lab. Here, I'd like to give you a quick intro to what an IP actually is. In the world of FPGA, an IP refers to a pre-designed and optimized hardware block. Think of it like building a house. Instead of molding your own bricks from scratch, you can directly use these prefabricated components. Take the clocking wizard we're using today as an example. It comes with pre-configured physical circuitry inside that delivers highly stable clock frequency conversion. This is far more precise and resource efficient than writing your own clock divider in Verilog code. Let's take a closer look under the hood. The 100 MHz signal provided by the onboard crystal oscillator is what we call the reference clock. However, because different circuit modules require different operating frequencies, we use a PLL for frequency synthesis. Inside the PLL, there is a voltage-controlled oscillator, or VCO. This oscillator continuously adjusts and calibrates its own output frequency until it achieves a perfect phase lock with the reference clock. This closed-loop tracking guarantees that the generated clocks are exceptionally stable, protecting our design from unwanted timing drift or jitter. You can download the required source code examples for this course from the link provided. For today's lab, we will be working with the following three files. Now, let's dive into the code implementation. We'll start with the module definition, where we define our inputs, the reference clock, the reset push button, and the gear shifting switch. We also define the 8 onboard LEDs as our outputs. The next step is IP instantiation. We'll declare the internal wires to capture the PLL output signals. Then, we connect the board's 100 MHz input to the reference clock port, run two output wires for clock 1 and clock 2, tie the reset button to the system reset terminal, and finally, lead out the lock status signal. Think of this process exactly like placing a prefabricated chip onto a physical board and wiring up its corresponding pins. To make the LED blinking visible to the naked eye, we set our target to count up to 100 million. We've implemented a 41-bit counter here, which gives us a very generous headroom. For clock 1 running at 100 MHz, counting to 100 million takes exactly 1 second. On the other hand, for clock 2 running at 200 MHz, reaching that same number takes only 0.5 seconds, meaning the flashing speed is effectively doubled. Next, let's discuss the counting logic. It's crucial to understand that these two always blocks for clock 1 and clock 2 execute concurrently, meaning they run completely in parallel. We utilize the pose edge, which is the rising edge of the clock, to drive the counter. Every time a rising edge occurs, the counter increments by 1, and it will keep tracking until it hits 100 million, at which point it resets to 0 and starts over. This is a classic, textbook application of sequential logic. Let's look at the two-stage synchronizer and see how to implement it. First, we establish our first register to capture the data value crossing over from clock 1 to clock 2. Then, with every rising edge of clock 2, the following logic is executed. If you look at this specific line of code, its purpose is to temporarily capture the clock 1 signal under the clock 2 domain, achieving our first stage synchronization. Next, we introduce a second register. This line of code stores the data that has just been stabilized from the first stage, effectively mitigating metastability and completing the second stage synchronization. This entire process is the fundamental concept of clock domain crossing. Let's officially get started with our project. First, open up the Vivado welcome page and click on Create Project. We will name this project Lab2_example. Select RTL project. Check the box for Do Not Specify Sources. On the board selection page, search for and find ZedBoard. Once finished, you will enter the main workspace. First, click on Add Sources from the left-hand menu. Choose Add or Create Design Sources. Click to create a new file here. And enter the file name, PLL_CNT. Now, we are going to introduce how to call an IP core. In the left-hand menu, look for IP catalog. Today, we need to use the clocking wizard. So we type clocking into the search bar. Double-click to open it from the list below. Once opened, you can see that we currently have only one default clock, clock 1. To add another clock output, click on the Output Clocks tab. Since we will be using a second clock domain today, let's check the box to enable it. Then, for its requested frequency, we are going to modify the value. Enter 200. This will give us stable clock outputs at 100 MHz and 200 MHz. Now, under the Design Sources hierarchy in the Sources window, you can find the clocking wizard IP we just generated. Next, we are going to write the Verilog code for PLL_CNT. Double-click to open the file, then copy and paste our code inside. Our next step is to set up the physical constraints. Click on Add Sources on the left menu again. This time, select Add or Create Constraints. Input the constraint file name, PLL_CNT. You can now locate this newly created file under the Constraints folder in the Sources window. Go ahead and paste our constraint code right here. Once completed, we will proceed with the logic synthesis in the left menu. Click on Run Synthesis. With that verified, we can now click on Generate Bitstream from the left menu. Now, click on Open Hardware Manager to enter the interface. Once you've entered the workspace, please follow the diagram to connect the ZedBoard using cables and turn on the physical power switch. At this moment, the green power LED will light up. Now, click Open Target at the top menu and select Auto Connect. Then, click on Program Device above. The blue configuration LED on the ZedBoard should light up now, and our custom counter circuit will begin executing immediately. Here is the final demonstration for Lab 2. Initially, the LEDs increment in binary format once every second to perform the count. We can flip the first slide switch on the right side to accelerate the counter. Now you can see that the LEDs are incrementing every half a second. Furthermore, if you ever want to reset the count, simply press the left button at any time to start counting from 0 again. Finally, here is a quick preview of our next lesson. We will explore Vivado's package IP feature, which allows you to wrap your custom RTL designs into reusable IP blocks for easy instantiation. We will also practice using Vivado's IP integrator to design block-based systems. I'm Albert. Thanks for watching, and I'll see you in the next class.